Hello friends, I, Pujanjali Shukla, class BSc first year, roll number 205047 of Isabella Thoburn College is going to explain you the topic Rolle's theorem. Rolle's theorem. If a function fx defined in a closed interval a comma b such that it satisfies the three conditions, that is fx is continuous in the closed interval a comma b, fx is differentiable over open interval a comma b, and fa is equals to fb, then there exists at least one point c such that a is less than c less than b, at which the derivative f dash c is equals to 0. Now we will state the Rolle's theorem. The theorem states that when the value of a and b are equal, then there exists a point c whose derivative at a point is 0. Here is a graph. Since the function fx is continuous in a comma b, it is bounded and attains its bound at least once in a comma b. Let its least upper bound supremum and greatest lower bound infimum be capital M and small m. Now we will consider the two cases. Case 1. If small m is equals to capital M, that is the maximum and minimum value are equal, then fx is constant function. fa is equals to fx is equals to fp is equals to capital M is equals to small m. F dash x is equals to 0 for all x belongs to a comma b. Then there exists c that belongs to a comma b such that the derivative f dash c is equals to 0. Now we will consider case 2 where m and small m both are distinct value, that is if maximum and minimum value are distinct. Suppose fx is maximum at c, then fc plus h minus fc and fc minus h minus fc both are negative where h is small. Here is a graph. You can see the value of fc is greater than the value of c minus h and fc plus h, and whenever we subtract a greater value from a lower, we always get a negative sign. So if h is positive, fc plus h minus fc upon h is less than or equals to 0. Applying the limits, limit h tends to 0 plus fc plus h minus fc upon h is less than or equals to 0. That is, the right hand derivative is less than or equals to 0. We mark it as equation 1. Now if h is negative, fc minus h minus fc upon minus h is greater than or equals to 0. Here both numerator and denominator will get a negative sign which will cancel out each other. So applying limits, limit h tends to 0 minus fc minus h minus fc upon minus h is greater than or equals to 0. That is, the left hand derivative is greater than or equals to 0. We mark it as equation 2. Now, since fx is differentiable in a comma b, it is only possible when left hand derivative is equal to right hand derivative. From 1 and 2, right hand derivative is not equal to left hand derivative, which is a contradiction. So, the right hand derivative is equal to left hand derivative when it is 0. So, f dash c is greater than 0 and less than f dash c. Hence, it follows that derivative of the function f dash c is equals to 0, where c belongs to a comma b. Hence, the Rolle's theorem is proved. Now, we will talk about the geometrical interpretation. The geometrical interpretation of Rolle's theorem. Geometrically, for if fx be a continuous function which possesses a graph and fa is equals to fp, then there exists a point or point between a and b at which f dash x vanishes, that is, at which the tangent to the curve y is equals to fx is parallel to the axis of x. Here are the two graphs from which we can understand. It is important to observe that if the condition of existence of the derivative is not fulfilled at a single interior point of AB, the theorem may not be valid. Now we will understand some example. First, verify Rolle's theorem for the function fx is equals to x square in -1 to 1. Since fx is a polynomial function, so a polynomial function is always continuous in closed interval and differentiable in open interval. Also, f minus 1 is equals to 1 is equals to f1. The value of -1 square and f1 square is equals to 1 always. So, all the three conditions of Rolle's theorem are satisfied. Then there must exist a point x is equals to c between x is equals to -1 and x is equals to 1 such that the derivative f dash c is equals to 0. So the derivation of x square is 2x. So f dash c is equals to 2c. Here implies 2c is equals to 0. C is equals to 0 lying between -1 to 1. Thus Rolle's theorem is verified. Example 2. Verify Rolle's theorem in 2, 4 for the function x square minus 6x plus 8. Since the function is polynomial, hence fx is continuous and differentiable in 2, 4. f2 is also 0 and f4 is also 0. The third condition is also satisfied. Now the derivative of f dash x is equals to 2x minus 6. Now f dash c is equals to 2c minus 6 is equals to 0. 2c is equals to 6. C, the value of c is 3. Hence c is equals to 3, that belongs to 2, 4. Hence Rolle's theorem is satisfied and verified. You can easily solve these questions by satisfying all the three properties which is told you earlier. Thank you everyone.